My name is Stephen Pratchner. I'm the program manager for the PIX CPU tools in the gaming division at Microsoft. In this video, I'll be walking through how to diagnose common CPU performance issues in a game that is sparsely instrumented with PIX events. We've probably all been in this situation. It could be that you just haven't taken the time yet to add much instrumentation to your title, or you may be looking at someone else's code, like middleware, for example. I have a sample title already running, so I'll start by taking an immediate timing capture that's long enough to give us several frames of data. If I start by looking at my main thread at the top, it's easy to see a pattern. I can see these groups of events all look to be about the same size and duration, and they all have space between them. So these are the events that I've used to represent a frame of CPU work. I'm going to select a few of these and drill in. So the first thing I notice is although I do have some PIX events defined, there really is not enough information to get more detail about what it all is executing during this time. You'll notice that my other threads have a similar pattern. There's a loader thread, a physics thread, and some renderers, all of which have just one top-level marker. So there are a few approaches I could take in this situation to get some more detailed performance data. The first option is to go back and add more events to my title using the PIX begin event API. There are a few drawbacks to that approach, though. For example, how do I know which portions of my title need to be instrumented to help solve the problem I'm currently investigating? I can guess and try a few things, but given that I have to rebuild and redeploy my title each time, adding additional instrumentation in a case like this can be very time-consuming. Instead, I'm going to use one of the new profiling features that has been added to PIX recently. If I go back and look at the options that are available to me when I start a timing capture, I see a checkbox that allows me to collect CPU samples. So I'll check that box and take another capture. So now when I zoom in, I can see information about the samples I just collected. PIX adds one lane for every thread to display the samples. The individual samples are represented by these blue boxes. PIX currently collects one sample per millisecond, but in a future release, we'll add the ability for you to customize the sampling interval. If I select one of these samples, the event details view on the right populates with the call stack for that sample. So this tells me which functions were running at this particular point in time. Now, what I'd really like to do is get more information about when some of the functions in this call stack are executed, without having to go back and add additional PIX events. I can do this using the checkboxes in this tracked column. So the first time I select one of these, PIX will ask me if I want to enable tracked functions for the next capture. I'm going to say yes. By selecting functions to track, I'm telling PIX to record every call to these functions the next time I take a capture. These calls will all be displayed on the timeline right underneath the PIX events and samples for a given thread. This is a very easy way to get more detailed information about what's going on in my frame without having to go back and add more instrumentation. I can also select functions to track using this stack analysis view. This view provides a roll-up of all samples collected per thread. So by expanding the row for one of my threads, I can see the call stacks that occurred the most often in the samples that were collected. Inclusive and exclusive percentages and counts are also provided. I can select functions to track by selecting them in the list and choosing the track button. So I'm going to select functions to track that have taken a significant amount of time. Now I'm going to go back and take another capture. Note that the Tracked Functions checkbox has been checked for me because I answered yes to the prompt. There's also this Managed Functions button. This button brings up a dialog that provides additional ways to specify which functions are tracked. We'll come back and look at this later. So now, when I take another capture, we can see that the timeline includes more data. So if I zoom into a few frames, I can now see information about all the functions that we're executing on my main app thread. However, I still have a gap of time here in the middle. It looks like there's not much happening in my frame at this point. At least it certainly doesn't match the pattern of the rest of the frame. So even though I've selected a set of functions to be tracked, there's still a reasonable portion of my main thread where I can't really tell what's going on. But thankfully, I have the samples. So if I select some of the samples in this empty window here, I can notice a few things. First, the call stacks all look the same, and the top of the call stack is always a call to physics synchronize. So this tells me that my main thread may be waiting on physics. And sure enough, if I go and look at the end of my physics work, you can see that it coincides with the point in time at which my main thread starts processing again. So, and remember, we've done all this analysis while the title was running. I never had to stop it, or make a code change, or rebuild. So earlier, I had mentioned this Managed Functions button. So far, we've been adding functions to track using either the stack analysis view or the event details view for a CPU sample. The Managed Functions dialog provides an additional way to add and remove functions from the list to be tracked. So when I bring up this dialog, I can see that the UI consists primarily of two list boxes. The list on the left is a set of functions that are available to be tracked, and the list on the right is the set of functions that are currently being tracked. You'll note that the tracked functions list has been populated with the functions that we tracked from our previous capture. I can populate the list of available functions either by loading a PDB from disk or by querying the running title. When I query the running title, PIX locates the PDBs for my title and populates the list of available functions with everything it finds in the PDB. I can now use the arrow boxes to move functions back and forth between the two lists. The boxes with the double arrows move the entire contents of one list to the other. The boxes with the single arrows only move the selected items. The list boxes also have filtering capabilities. In this case, since we're interested in physics from the last capture we took, I'll use the filter box to find all functions that appear to be related to physics and add them to the list of functions to be tracked. So now, when I go back and take another capture, and drill into a frame or two of physics work, I can now see all of the functions that executed during this frame related to physics. So in this video, we've taken a look at the features and timing captures that can help you diagnose issues even if your title has very little instrumentation. We've collected CPU samples and we've tracked some functions in order to get more detail on what code is executing during a frame. And we were able to complete the entire analysis without ever having to stop or rebuild the game. Thank you for listening.